Hello guys, welcome everyone. Today I am here to give a presentation on CL for symmetrical and cambered airfoil. Now I will give a small introduction of myself. My name is Jisana Reddy, having a pin number of 21955A2109, and my topic is CL, coefficient of lift for symmetrical and cambered airfoil. Abstract after my presentation. In this presentation we will discuss about symmetrical and cambered airfoil along with the coefficient of lift, and we discuss some terms related to this. Introduction. Now let us consider the 2D cross section for a finger. In this figure we can able to understand, in this figure the airfoil nomenclature has been represented neatly, in which the distance between the trailing edge to leading edge is known as the chalk chord, and next the top point of the airfoil is known as the leading edge, and the end point of the airfoil is known as trailing edge. By using the figure we can able to understand that detailedly. And next, the mean camber line is the locus of points halfway between the upper and lower surfaces measured perpendicular to the mean camber line itself. The most forward and rearward points of the mean camber line are the leading and trailing edges respectively. The straight line connecting the leading and trailing edge is a chord line of the airfoil, and the precise distance from the leading to a trailing edge measured along the chord line is simply designed the chord C of the airfoil. The camber is the maximum distance between the mean camber line and the chord line measured perpendicular to the chord line. And next, the thickness is the distance between the upper and lower surface also measured perpendicular to the chord line. Next, concept for airfoil behavior. And next, the aerodynamic center, which is a chordwise location, which the pitching moment is independent of the lift coefficient and the angle of attack. The center of pressure, which is a chordwise within the pitching moment is momentarily 0. On the camber location, the center of pressure is not a fixed location as it moves in response to changes angle of attack and lift coefficient. Airfoil. An airfoil of aerofoil is a cross-section shape of an object whose motion through a gas is capable generating significant lift, such as ring, rotor, etc. Next, there are different types of airfoils. They are symmetrical airfoil, and in the figure we can able to understand it is a symmetric airfoil, and the cambered airfoil. And in this figure we can able to understand the cambered airfoil. Next, coefficient of lift for symmetrical airfoil. As per Kutta-Jakov's theorem, we find that the lift per unit span is equal to rho v r, where the rho is mean the density of free stream air, and the next symbol is represented to the total circulation, which is equal to pi into alpha into cv, and the v is its velocity of air, and the c is surface area. And next, by solving the above equation, we get CL is equal to lift per unit span by dynamic pressure into area, where as you know the surface is equal to C plus C. By substituting the lift per unit span value, the above equation we get CL is equal to 2 pi alpha rho v square by rho v square. And by solving the equation we get CL is equal to 2 pi alpha. Next, therefore we can able to confirm that coefficient of lift for symmetrical airfoil CL is equal to 2 pi alpha. So therefore the coefficient of lift for symmetrical airfoil is 2 pi alpha. Now let's consider the other example. Now as per the Kutta-Sekos theory, and next as per the Kutta-Sekos theorem we find the theorem. Okay, done. We get, and now let us calculate the coefficient of lift for cambered airfoil. As per the Kutta-Sekos theory, as we know that the lift per unit span is equal to rho v r, where rho v square c. We get this because as we know that rho is equal to something where the lift per unit of span is equal to c, and density, and rho represents the density of free stream, and the r represents the total circulation, where c v alpha a0 plus alpha by 2 a1, and velocity v is represent the velocity of air, and c represent the surface area. And next, by solving above equation, we get CL is equal to lift per unit span by dynamic pressure into area, where S is equal to C1, and we get, by substituting the value, the lift per unit span value, then we will get CL is equal to pi by 2 A0 plus 2 A1. Therefore coefficient of lift for cambered airfoil is CL is equal to alpha by 2 A0 plus A1. Conclusion: coefficient of lift for symmetric airfoil. A symmetric airfoil is CL equal to 2 pi alpha, and next the coefficient of lift for cambered airfoil is CL is equal to pi 2 A0 plus A1. Thank you. In this, by this experiment, we can able to conclude that in this the airfoil is a device in which it generates the amount of lift when a flow is passes over it. It is capable to generate the amount of lift. And next, and the airfoil is furtherly classified into two types: symmetrical airfoil and cambered airfoil. By this presentation we can able, and this presentation is to calculate the coefficient of lift for symmetrical airfoil and cambered airfoil. And the symmetrical airfoil, also known as in the name itself, it will define us. It will, at the x-axis, it will perfectly overlap each other, and by the end of this presentation we can able to confirm that the coefficient of lift for symmetrical airfoil CL is equal to 2 pi alpha, whereas the coefficient of lift for cambered airfoil is CL is equal to alpha by 2 A0 plus A1. This is the end of the